Okay, so it seems that this is the last lightweight part of this course about random number generation support in C++11. So let's start with let's say the C version for random number generator. So basically, until C++11, if you want to do random number generation in C++, let's say in a native way, basically you have to use some components of the C standard libraries. So C standard library, basically, I'm pretty sure that you have already seen this kind of code. It is the Wikipedia example or something like that. So basically, here we are generating double random numbers in the interval between 0 and 1. Okay, we do that by making the calls to this rand function that gives you a random number in the interval 0 randmax, where randmax is a macro that expands to an integer constant, which is the maximum value returned by the rand function. And the other function that we have to use here basically is this one that it is required to set the seed, basically to initialize the random number generator. So this is basically what we have to do if we want to do random number generator in C++ without external libraries, basically. The problem with this method is basically that the underlying algorithm for the generation of random numbers is unspecified, and this is not good. And the other problem is that the random sequences produced by this function are known for be of very low quality. So they are good if you are just making some small example, but if you are doing real science, then you need to use something else. C++11 provides a new support for native random number generation, and basically everything is included in this random header. And it is based on two components, which are also the two main elements that we are using when you do random number generation. The first component is an engine, which is basically responsible for the generation of random sequence of pseudo-random sequences of bits. And the other element is instead the distribution object, which is responsible for the generation of random number, starting from this pseudo-random bits sequences, and random numbers that are distributed according to a given mathematical function, or distribution of Poissonian distribution, or Gaussian, or something like that. So this is exactly how their new support in C++11 for random number generation is based, actually. So if you want to translate the previous example in using the new facilities provided by C++11, basically you will end up with something like this. You have, of course, to include the random header. Then you have to initialize a random engine, which in this case is this default random engine. Then we will see which kind of engine are included in the standard library. And here we are using the constructor which takes in input the seed. Then you have to create an object representing your distribution, which is in this case it is an uniform real distribution, so that we want to reproduce the previous example. And we are using the constructor providing the range for the generation of the random numbers. And then to generate a random number, you have to make a call to the parentheses of operator of this object that takes in input the random engine. And that's it, basically. So what about the engines? Yes. Okay. So basically, you have two ways to initialize an engine. You can use the implicit default initialization, which means that basically you are using the default seed for the random engine. And then you can use also another constructor, which is the one that I've used in my example, which takes in input the seed. You can also reset the seed after that you have created your instance of the generator by calling this seed method, or you can also reset the seed to the default value using this one. Oh yes, there is I think this is interesting. What if you need basically, if you want to make different run and every time you want to use to produce different random numbers? This is something that you always need if you're trying to do some real world calculation, want to make, I don't know, random Monte Carlo integration or something like that. You need every time for different runs, you need different sequence, of course, of random numbers. Basically, if you use let's say the traditional way is this one. Basically, you need a different seed for the initialization of your engine every time. So with the old C style, what you can do is something like that. This is a a function that provides you the time, the system clock time, basically, so that every time that you launch, submit, or you execute your job, basically in a different time, basically you will have a different seed. But there is a problem, of course, with that, because if, for example, you're submitting to a lot of jobs in the same moment, basically all your job will probably get the same value for the seed, so that you will have a kind of replicated job that are actually useless. Another possibility is instead using something which is a source of entropy, which is system specific, like this file from for the Unix case, which is basically, it is a special file that every time you access it, it provides you a number which is somehow calculated, making use of information provided by devices and sensors which are somehow connected to the system. So it is a kind of measure of an environmental noise. So basically you will get a random number that can be used here. You have something which is similar to this one, but in a more, let's say, standardized way, which is this object in C++11, which is the random device object. You can create an instance of this object in your code, and you can pass it to the default random engine, calling the operators parentheses, so that you will provide to your engine, let's say, a random seed for the initialization of the random number sequences. The problem here is that you cannot be sure of which device you will get. Actually, it is implementation dependent, the fact that there could be a constructor of this random device object that takes in input a string that gives you the possibility to choose a particular device to be used for the initialization of the random engine. So in the standard library, we have now different possible engines of different quality, speaking about the quality of the random sequences that are produced, and also of different cost from a computational point of view, of course. So this default random engine, that is the one of our example, it is, let's say, the one for the lightweight use, so the random sequences are not very good from the quality point of view, but it is computationally with a low cost from a computational point of view. You can have good quality engines, which are somehow in the middle between this low quality and the best one, which have a bit, let's say, higher cost from a computational point of view, but they provide a bitwise identical sequence of random number in the different implementations, so that it is good if you're trying on different platforms and so on. I don't know if we have some particle physicists in the room, but this is, I think, the most famous in our case. I'm a particle physicist, so this is why this is the Ralux case, which is okay. So we have different possible engines. And then we have another set of engines which are the best one, let's say, the one that gives you the possibility to better, let's say, configure the generation of these random sequences, and are these classes templates that takes in input as a first template parameter the engine, one engine, basically, and then some other parameters. Basically, what they do is to take the sequences of random bits generated by these engines and do something, let's say an additional processing, just to produce better random sequences. But if you're very curious about this stuff, you can have a look. I have no idea actually what they are doing in the specific case. The engines have some additional capabilities that I think that are quite useful if you want to use that for your work. Basically, they have an internal status, of course, which represents the status in the sequence of a random number that they have generated that can be saved and restored, basically using the stream operator, which means that you can do something like that. Let's say that we are using this default engine. We have generated a set of random number. Then at some point we can do something like this, which basically allows you to store the status of the random engine on a file, for example, and this status that can be restored. And this is quite useful, of course, if you need to create some checkpoint files during your simulation, because you can restart the simulation exactly from the point of the checkpoint file, basically. OK engines of the same time can also be compared. Basically, there is an implementation of equal operator that gives you the possibility to check the status of two engines. They basically make a comparison of the internal state. And you can also discard a set of numbers, basically, if you want to make a kind of selection on the sequence of random numbers that are produced. And what about distribution? So as I told you, you have to use These random engines basically together with distribution that gives you random number distributed according to a given mathematical function. We have 5 family of distribution. I will not give you all the detail, but you can have an idea. We have the uniform distribution for integer and for real type, Bernoulli distribution, so in particular geometrical and binomial, for example. We have the Poisson distribution, normal or Gaussian distribution, and all the, let's say, the derived distribution from the normal one, so Cauchy, chi-squared, the log normal, and so on. They are also class templates, and the template parameter is always the type of the number returned by the distribution itself, which means that basically if you have a normal distribution, of course, the normal distribution is defined to produce floating point numbers. Yes?
For the distributions that are not known analytically, like normal inverse or something, does the standard prescribe what algorithm to use?
Oh, I don't think so. For sure, you can define a new distribution that can interoperate with the engines and so on if you respect some standard.
I'm just wondering, if I run the normal inverse, let's say, on 2 different compilers for the same input number, am I guaranteed to get the same result or not?
But this should be implementation dependent, right?
That's
because
the question.
It's not. I mean, it is no that it's true that maybe you don't have an analytical formulation, but it's somehow it should be defined in a well-defined.
Well, there are approximations to different degrees of precision, right? So the question is, does the standard prescribe which of those to use?
I don't have an answer for this question, so I have to check. I don't know. Let's check. Okay. Yeah. You have no idea. Yeah. Okay, so the distribution are basically template class, and the template parameter is the type returned when you do the random generation. So if you have a normal distribution, of course, you will have a random number that are floating point numbers, but you can decide between double, float, and so different precision. And the same is true also for the Poisson distribution, let's say integer value distributions. Distribution have two different constructor. Oh, sorry, no. Distribution has 2 different methods for the generation of random number. The first operator is the one that takes in input the generator. That is the one that I was showing you in the example. And there is another one which also takes in input a set of parameters, which basically are the parameter that defines the mathematical property of the distribution. So if we have, for example, a normal distribution, which means that in this case you will provide this param type that, as we will see, will contain these 2 numbers, the mean value and the standard deviation, of course, and the same also for the other distribution. Distribution has also have 2 different, basically 2 specific different constructor depending on the property of the distribution, so that, for example, for the normal distribution, you will have a constructor that takes in input the 2 parameters that define this kind of distribution. And in case of the Poissonian distribution, we will have just 1 input parameter which corresponds to the mean value. So in the previous slide, I was already using this param t parameter as input type for the generation operator. Basically, this is a nested type that is defined so within the distribution using the same name. It is basically a bundle of the parameters that defines from a mathematical point of view the property of the distribution. So it means that basically for the Gaussian distribution, this param type will be something like a structure that contains the mean value and the standard deviation. In case of this uniform distribution, this will be an aggregate type which contains the minimum and the maximum value of the range of generation of number. The parameters of the distribution can be, let's say, assigned when you create the distribution, calling the constructor, but then you can also change them at, let's say, when you start to use distribution in a temporary way. So in this case, for example, we are generating a random number from this distribution D1, which is defined, okay, it is the uniform distribution. Here we generate a uniformly distributed number, providing this parameter bundle P, which is defined here, for example, and this is a temporary change of the properties of the distribution. Okay, only for this number that we are generating here. If you want to change, let's say, permanently the properties of the distribution, you can just call this method .param that will give you a permanent change in the distribution properties. Of course, you can also access the parameters that describe the distribution. So basically, you will have a specific method, let's say, depending on the distribution that you're working on. And for example, for a normal distribution, we'll have, for example, the mean and standard deviation method that will give you these two parameters, of course. Very quickly, also the distribution has some additional capabilities that are quite similar to the one of the engine, so that also for the distribution you can make a comparison, and basically this comparison operator will make a check on the parameters of the distribution, so mean value and standard deviation, for example, for a normal distribution. It will not make a check on the engine status, because the engine is not part of the distribution. It's always an input parameter that you provide to the parentheses operator when you need to generate a random number. But there can be also other kind of information as internal status of distribution. This is a good example. This is an algorithm that allows you to generate a random number for a normal distribution, and the generation of random number in this case is a pairwise. It's better from a performance point of view with respect to a single random number generation for the normal distribution. And basically, when you do something like that, you are creating every time a pair of random number generation. The first call for the random number will give you back, with the first call, the distribution will give you back the first number of the pair and will store the second one. And with the next call, you don't have to generate another random number, because the distribution will give you back the second number that has been stored in the previous call. So in this case, this second number basically is part of the stored status, and also part of the status that is compared when you use this comparison operator. And also it is the status, part of the status that is stored, for example, if you try to save, also in this case, the status of the distribution for your checkpoint files or something like that. We are almost over. I just want to tell you two things. The one is about generator meteors. Suppose that you want to generate a random number within a given interval, define it like this. You can think about doing something like that. You can create a function that takes in input your parameters for the interval limits, and then you can, instead of using the distribution, you can think about directly using a random engine. And you can do something like that. Okay? This is in general a bad idea. Yeah. Okay. This is in general a bad idea because by definition the engine is only required to span two values. This is enough if you use the engine with the distribution provided by the standard template library. But if you do something like that, basically two values are not enough to do a good job here, because you need at least this b minus a plus 1. And the other problem here is that the reminder operation that you are using here to normalize the number that are generated by the random engine basically makes the lower number a bit more probable, a bit more likely than the bigger one. So you are basically introducing a bias. So the take-home message here is always use a distribution with the random engine. And the last point is about sharing an engine in different points of your code. So let's suppose that you want to use the same engine in different scope, in different part of your code. I'm just separating here using the part of code using the scope. You can do something like that, basically. We have a getEngine method that returns a reference to a given instance of a random engine, and you want to use here and here the same random number, the same engine, of course. You can do that. You always have to remember that, of course, if you do every time that you make a call of a random for the generation of your random number in the first scope, you are also modifying the status of the engine that will be used in the second one. This is perfectly fine in a single thread problem, in a single thread code, of course, but you have to remember that if this scope are not the single scope, the scopes of a single thread, but are part of two threads, here you don't have any kind of built-in protection for thread safety. So you can have of course a race condition in the status of the engine, and so you have to introduce some kind of protection if you want to do something like that with multi-threading codes. So it was quick, as I told you. So
I quickly checked, and I didn't find in the standard anything about distributions, and also checked on Stack Overflow. Apparently, so you have reproducibility of the implementations for the engines, so the Mersenne, Twister, etc., but it's not, I don't think it's guaranteed for distributions. So the distribution implementation, from what I've seen by looking quickly, there's no guarantee that you get the same results with different compilers, or the different degree of accuracy, let's say.
But
as far as I know.
do you know if the algorithm must be always the same? It is just a matter of, let's say, calculation that can introduce some precision issues?
Even the algorithm? I didn't see the sentence say you should use this algorithm for doing this
so it means that no.
distribution, which means basically each implementer will use a different thing. Now, it might be that they share the code and everyone uses the same, but it's not guaranteed.
Okay. Any other question? No? Okay.